Hi, this is Tzvi Rosen. Now that we're well into the course and we're familiar with rings, we're going to introduce modules, which behave with rings as vector spaces do with fields. So let's go for it. Okay, here's a brief outline of this lecture. We're going to start with some first definitions, then we're going to cover module homomorphisms and quotients, and finally we'll look at some operations on submodules and modules. Okay, first off, definition of a module. Let's let A be a ring, and we're going to let M be an abelian group, okay, and the operation will be addition, as it generally is with an abelian group. And we're going to introduce a multiplication map. So let phi map A cross M to M. So you can just think of this as A multiplies an element of M and gives you a different element of M. And this map satisfies, so it'll be a map satisfying the following. So we want the ring operations and the module operations to behave nicely together. So we're going to have distributivity over the group operation of the module. Okay, so this is going to be equal to A dot M1 plus A dot M2. And obviously this is for any A in A, and for any M1, M2 in M. Okay, so just as it has to behave nicely, the ring multiplication has to behave nicely with module addition, it also has to behave nicely with the ring operations. So we're going to have A1, A2, M. Okay, so if you multiply the ring, if you multiply it in the ring first and then carry out this multiplication map with the module, that has to be the same as if you did one multiplication by the module and then did another. Okay, so same deal. Okay, it respects the ring multiplication. Obviously, it will also respect the ring addition. So if we have A1 plus A2 M, this is going to be equal to A1 dot M plus A2 dot M. Okay, and there's some subtlety here, right? So this addition is in the module, and this addition is in the ring, but generally it doesn't make a big difference for us. Okay, so, and this has the same quantifiers as the line above. Finally, we need that if you take the multiplicative identity element in the ring, oh, I forgot that we're calling our ring A. This is A, this is A. And you act on any element of the module, you should get that element back. So for any x and m. Okay. And whenever I see these kind of these axioms that involve the identity, it makes me think whether you really need that axiom, whether you could infer it from some of the other things. So let's consider that question. Is that last axiom necessary? And indeed it is. You could have something weird where, let's say, so one thing that would have to be, we know that A1, A2x is going to be equal to A1, A2x, where you put parentheses here and here. So in particular, if you have the identity times itself, that's obviously just the identity. So that's going to be the same as the identity acting on x. Okay, so in other words, this is going to be equal to this. But that doesn't mean that the identity, the ring identity, acts as the identity on the elements of the module, because it could just mean that it's a projection operator, right? This tells you that it's idempotent, meaning if you do it once, it's the same thing as doing it twice, but it doesn't tell you that it's actually an identity. And so you could think about something like, you know, if your module is a, let me write this here. We'll see, for example, that vector spaces are modules. So if your module is k2 for some field k, you could have 1a acting on x, which is a vector in k2, so it would be x1, x2, and you could just act by projecting onto the first coordinate, for instance. So this could be x1, 0. So because of weirdness like this, you don't want this to be the case. You don't want the identity to go from the identity acting on this module element to go from a more complicated module, and now just acting with the identity sends you to a submodule. That's not going to work for us. So for that reason, the last axiom is necessary. Okay. So one thing I want to point out is that instead of these detailed axioms, another way you could describe this as would be to say, okay, we have our ring A and our abelian group M, and now instead of having a multiplication map, which we treat as a map from the direct product A by M to M, what we're going to do is have a map. So we're going to define a ring homomorphism from A to the endomorphism ring of M. Okay, so this is the ring of maps from M to itself, with composition as the multiplication operation, and addition as element-wise addition. And if this this is a ring homomorphism, then this uniquely determines multiplication. Because you can treat every product A dot x, where A is in your ring and x is in your module, this is just phi of x. Okay, so that's, sorry, phi of A, excuse me. So now this should be an element in the endomorphism ring of M, and then you apply that to x, which should be some y, an element in your module. Okay? So this is another way to define a module, and here all of the axioms that we listed here with all of the operations being respected, that's just a consequence of the properties of ring homomorphisms. Okay. So let's do a few examples of modules. So one pretty straightforward module is ideals. So if you have a in A an ideal. So you can just use the standard, instead of a special new multiplication for elements of the ring by elements of your module, just use the standard A multiplication. Okay, and because the ideal, so since A is closed under A multiplication, this will remain in the module, or this is well defined. This is well defined. Okay, and obviously it's an abelian group, since it's a subgroup of the additive group of the ring. Okay. Another example of a module is an abelian group. So if you have G abelian, and these all appear in Atiyah McDonald, by the way, I'm not coming up with these randomly. If you have G an abelian group, then you can think of G as a Z module. And multiplication by Z is just, so if you have NG, this is just G added to itself n times, okay, which has to be legal because it's an abelian group. And minus G is or minus NG is just the same thing, but you use the additive inverse of G, which has to be in there because it's an abelian group. Okay, so in this way, we have this well-defined Z multiplication by our group. One last one here is if we have K a field, then vector spaces over that field. So if V is a K vector space, then just with the standard, our standard notion of scalar multiplication in linear algebra, this is a K module. And really, this is the intuitions from linear algebra should guide a lot of what we do in module theory. Okay, so here's a slightly more complicated example. If you take modules over the polynomial ring in one variable over a field, K, then that's equivalent to K vector spaces with a linear map. So how is that the case? So we want to consider what happens. So let's say we have so let's let V be a K module, sorry, KX module. So that means we have to have some well-defined multiplication of these polynomials by elements of our module. Okay, so that means that P of X dot V, this is going to be some collection an x to the n plus up to a1x a0 dot V. And this is going to be an element in our module as well, so this has to be some vector. And we have linearity with everything, so we can think about, this is an x to the n applied to V, plus up to a1x applied to V, up to, and then a naught times V. And all of these should be elements of the field, so the AI are in K. And by one of the axioms of the of the module, you have to be able to multiply. So for instance, for x to the n, I need to be able to do one multiplication by x at a time, right? So this is really an x dot 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 x dot v, etc. a1 x dot v plus a naught v. And what we're seeing here is that x dot v. So once we fix, so x dot v defines some map of the module to itself. Okay, and it has to be linear if we apply the module axioms. Okay, and then the rest of the polynomial's action can be determined just by iterating that linear map. Okay, in particular, so you do x once to get, for instance, x dot v. In the case of x to the n dot v, so do x once, and whatever that result is, do x on that, okay, etc., etc. So this is also a linear map, but it's always going to be expressed in terms of polynomials in this linear map, x. Okay, so one more example to mention is kg modules. So remember, kg is the group ring with coefficients in k. So recall, kg is not commutative. Okay, and we're assuming here that g is, let's say, for g non-abelian. But still using this as a good motivation for talking about modules, these kg modules, we can think about how an element in the group algebra, in the group ring, acts on an element of the module. So if you take, so an element in the group ring looks something like a1g1 plus up to a(n)gn. This is just a formal sum of elements of the group with coefficients in k. So ai is in k again. And this is going to be acting on x in our module. Then we're going to have a1g, g1 acting on x, plus, etc., a(n)gn acting on x. Okay, and the module axioms here are going to translate into the representation, the axioms defining a k representation of the group. Okay, and you can also get this straight out from our definition above of the map to the endomorphism ring. So here, what we're doing is sending G to a map of, sorry, what are we doing? We're trying to map the group ring to the endomorphism ring of Kn, where K, where I guess we should really take M to be arbitrary vector space. We don't want it necessarily to be finite dimensional, and this is really exactly what the what representations are. Okay. It's modeling a group as a group of automorphisms of a vector space. Okay. So you might object that group representations are generally homomorphisms to the automorphism group of the vector space. And that's true, but because you can think about how every group element also has an inverse, so at least those generators will be mapped to automorphisms, and then that will generate, that will determine the rest of the homomorphism. Okay. Okay, so those are some examples of modules over various rings. And now we can go into some detail about aspects of module structure. So a submodule, so if you have, let A be a ring, and M is an A module, we say that N in M is a submodule if N is a subgroup under, like, given the abelian group structure of the module, and it's closed under multiplication by A. Okay. Okay, so we have submodules, and we can define module homomorphisms. Okay, so if you have, let M1 and M2 be A modules, okay, then we want homomorphisms to satisfy to interact well with the structure of A modules, as we would hope. So phi, a map from M1 to M2, is a homomorphism, a module homomorphism. If, okay, first of all, it needs to be a group homomorphism. So phi of x plus y equals phi of x plus phi of y. And it needs to respect multiplication by A. So we get phi of ax equals a phi of x. Okay. Now we can talk about the kernel and image of this map. So the definition also makes a bit of a claim, so we're going to claim first that the kernel of a module homomorphism, so actually let's, for the sake of notation, let phi from M to N be an A module homomorphism. Then the kernel of phi, which is defined as the set of elements in M such that x maps to 0. This is a submodule of M. Okay, and that's not too difficult to prove, and let's prove it quickly. If you have two elements of the kernel, and you want to see given, so let's let x and y be in the kernel. then phi of x plus y by the properties of a homomorphism will be equal to phi of x plus phi of y. But since x and y are in the kernel, this means that they're both mapping to 0, so their sum is also 0. As for a and x in the kernel, if you have phi of ax, by virtue of the homomorphism, you have a phi of x. And since that maps to 0 and anything times 0 is 0, that gives you 0. Okay, and let's make a bit of room for the next definition. So we're going to define the image of phi, as we generally do, to be the set of elements in N which are for which there exists some x, such that phi of x is equal to y. And this is also a submodule. And also not too hard to check if you have x and y in the image. That means that there are v and w mapping to them. But then, if there are v and w mapping to them, when you add them together, you get x plus y. Okay, so that means it's closed under addition. As for multiplication by an element of A, well, because you have v mapping to x again, if you take phi of AV, that'll give you AX. Okay, so it's closed under addition and scalar multiplication, so multiplication by elements of the ring, so that tells us that it's a submodule. Okay, so now that we have a notion of submodules, we can talk about module quotients, and it's pretty much an application of the theory of quotient groups. Okay, so if n in M is a submodule, we can define M, I should say an A submodule. We can define M mod n as the quotient group and it also happens to be well defined as an A module. And the reason it's well defined as an A module is because we restricted submodules to be closed under A multiplication. So let me justify this claim. And to justify that this is well defined, we want to show that if we take two representatives of cosets, so that means, let's say we have x plus n is equivalent to x prime plus n, that means that x is equal to x prime plus some element of that submodule. But when we multiply by an element of A, so AX will be equal to AX prime plus AN. We know that AN is also in N by virtue of N being a submodule. So this means that AX will be equivalent to AX prime mod n. Okay, so that tells us that this is well defined as an A module. Okay, so now that we've defined quotients, we can define the cokernel of homomorphism. So if we have, again, phi from m to n, a module homomorphism, and these are both A modules. And then if we take the quotient, so define the cokernel of, or written coker of phi to be equal to n modulo the image of phi. Okay. So you can think of this as stuff that's not mapped onto, or kind of the complementary submodule to the stuff that's in the image. You have the complementary submodule, and together they span the whole module. Okay. In addition, because we have quotients, we can observe that a lot of the so all of the standard isomorphism theorems for groups carry through to modules. So isomorphism theorems for groups apply. These are often connected to Annihilator, who made their importance very popular. So I think that she wasn't the original one to publish them, but she did the most with them. So these are the isomorphism theorems of groups, and they apply to modules. Apply to modules. In particular, if you look at the quotient modules, so you get m mod kernel of phi will be isomorphic as a module to the image of phi. Okay. Okay. Let's look at a sample homomorphism, and we can think about the kernel and the image and the cokernel. So if we're looking at 2z mapping to z mod 32z, and add a little line there, and this is going to refer to, we're thinking of both of these as z modules. So this is a homomorphism of z modules. Okay, and both of these are z modules. The first one is an ideal, and we know ideals are of a ring are modules over that ring. And the second one is a quotient, and certainly a quotient of a module by a submodule. And since a ring is a module over itself, and the ideal is a submodule, will also be a module. So we have a homomorphism of z modules sending 2 to, let's say, the equivalence class of 4 in z mod 32z. Then how does this work? So what's the kernel of this map? So the kernel will be a set of elements mapping to 0. And so since 2 maps to 4, and 32 will map to 0, or rather, when the image is 32, that's equivalent to 0, so we'll be mapping 16 to 32. So the kernel will be 16z. Okay. The image of phi, because you're sending the generator of the module to this to the element 4, so everything will be in the span of 4. But that's just a subgroup or an ideal of this ring. So this will be 4z mod 32z. And as we know, this is isomorphic to z mod 8z. Okay. As for the cokernel, we want to take the image module, or rather the target module, and quotient out by the image. So So we have z mod 32z modulo 4z mod 32z, and this is going to be equal or isomorphic to z mod 4z, and that's another isomorphism theorem that you can apply. In terms of the isomorphism theorem we made note of on the previous page, that the module mod the kernel is isomorphic to the image, you'll note that so m mod kernel of phi is 2z mod 16z, which obviously is isomorphic to 4z mod 32z, which is the image. Okay, so that's an example of a module homomorphism and some of the associated submodules. Okay, now we're going to look at some operations on submodules. So the first one is a sum of submodules. So if you have a collection of submodules in a module, be submodules of a module, so then you can define the sum of submodules sum of mi will just be equal to the set given by sums of elements of each of the mi. Where xi is in mi. Okay, and this addition is well defined because these are all in the same submodules of the same larger module. Okay, so that's the sum of submodules. So a module generated by a single element together with multiplication by a is called a cyclic module. So if you have m equals ax and this is also, you can also write this as the set of Rx, where R is in A. This is called a cyclic module. Okay, much like a cyclic group, it's generated by a single element, though with a cyclic group, you only have the group operation, but here you also have multiplication by a cyclic module. Okay, and if m is a sum of cyclic modules, it is called finitely generated. And finitely generated modules are going to be really important for us. Okay. Another couple operations on modules. So if you have, again, we have some collection of submodules. The intersection is exactly what you would expect it to be. It's just the set theoretic intersection. And this also has the structure of a submodule. Okay. As for product, so unlike with ideals, where you have the ring multiplication to multiply elements of the ideals together, with modules, there's no well-defined multiplication in a module. You only have the addition. So what do we mean by a product? This is going to be an ideal. So if you let A in A be an ideal, and you have a module M, So then you can talk about the module, which is the product of that ideal by the module M. And this is an A module. All right, and you can think about how it's closed under under multiplication by A, because any ideal elements of the ideal, or rather the ideal is closed under multiplication by A. So same property pretty much. And that's what we mean by a product of a module by an ideal. Okay, now let's define a colon ideal. So we've seen this in the context of ideals. You'll recall, let's do a different color. Recall that if we have two ideals in a ring, then we had this quotient which was the ideal defined as the set of elements x in A such that xb is contained in A. Okay, and that was called the ideal quotient, sometimes called the colon ideal. Okay, so we're going to make a similar definition for modules. So for M contained in N submodules, define N colon M, or rather, no, sorry, the other way around. Define M colon N to be the set of elements in the ring A. Okay, so these are both A modules, such that Xn is contained in M. All right, because we're sending it to a submodule of itself by multiplication multiplication with elements of A. Okay, so this is called the colon ideal associated to this module and its submodule. Okay, so if one of those modules, so if M is the 0 module, then 0 quotient N, whatever the larger module is defined or is denoted as the annihilator of N. Okay, and a quick example of that would be if you have N equals, we can use the same ring as before, Z mod 32Z as a Z module. Then 32Z would be the annihilator. Right? Because whenever you multiply anything in the module N by a multiple of 32, it immediately goes to 0. Okay. So if M is a module with the annihilator equal to the 0 module, then M is called a faithful module. We'll finish off with two constructions. These are the direct sum and the direct product. So before, with the sum of submodules, we were using the addition inside of the larger module, okay, which obviously had its own addition. But we can define a direct sum with modules that are not inside of a common module. So suppose we have some family of modules. Let Mi be a collection of A modules, and we'll let I be in an arbitrary index set, possibly infinite. Be A modules. Then the direct sum over the index set of Mi will be equal to the set of formal sums of elements of the constituent modules, where xi is in Mi, and all but finitely many xi are 0. Okay. On the other hand, if we take the direct product, so here we usually denote this as a sequence. So again, this will be over the index set. This will be a sequence of xi for I and I, where each xi is in Mi, but we don't have the restriction that finitely many of them have to be 0. And we should note that these are not equal. These are equal in the finite case, when I is a finite index set. Or I should say isomorphic. They define the same object, because you could just replace the formal sum with a sequence, and the restriction that finitely many, all but finitely many are 0, doesn't have any effect. But if you take, for instance, I to be a countable infinity, so I equals z, for instance, then the cardinality, so and let's say we have I forget what modules there are, some non-trivial module, then the cardinality of the direct sum is going to be countable. Whereas the cardinality of the product is uncountable. Okay, so these are not equal as long as we're looking at infinite index sets. Okay, and that's all of the module equipment I wanted to give you today. We'll do some cool stuff with modules next time. All right, thanks so much.